So, and he's a professor of computer science, and he's very active in the space that we care about, which is pretty much the intersection of information retrieval and natural language processing. So I met him at the ECIR conference series that we regularly monitor and attend and publish at. And he actually got multiple awards for the things that he's presenting to us today. So he's extremely successful. He got Best Short Paper Award, Best Demo Award, even in the same conference for the same thing. So great welcome, Ricardo. And you will probably show some of your team. But yeah, great to have you here virtually. I wish we could host you in person, but not this year, I'm afraid. So hopefully soon again in person. But thanks for presenting to us. And yeah, the floor is yours, please.
Okay, thanks a lot for this kind of introduction, and hello to everyone. It's my pleasure to be here. Like Jochen said, I'm okay. Here it is. So I'm from Portugal, and I live in Covilhã, which is a city in the center of Portugal, which is also known as the old Portuguese Manchester due to the importance of the textile factories in the city in the past. And I think this might be a very curious fun fact for those who live in UK. I don't know if we have people from abroad. And like Johnson said, I'm a professor at the Polytechnic Institute of Tomar, where we have two campus. So one is in the beautiful city of Tomar, which is best known for the famous Convent of Christ, a World Heritage Monument whose construction dates from 1160. And you are more than welcome, obviously, to visit us when the COVID-19 is over. And we also have another campus in the city of Abrantes. It's a very welcoming city that also worth a visit. And like Johnson said, I also collaborate with the Porto Business School, which belongs to the University of Porto. I'm also a researcher at INESTEC, which is one of the biggest research centers in Portugal, with more than 700 researchers. So INESTEC is located in the well-known beautiful city of Porto, which I believe some of you have already had the chance and the pleasure to visit before this crisis. So I can say that from time to time, I do this bi-directional route. And finally, and as a joke, while I'm not working, which doesn't happen that often, I like to go to the Algarve, where I can find some of the most famous beaches of the world. The difference here is that I don't have any row back home, and you can figure out why by looking into this picture. Anyway, you can imagine after these 3 slides how many kilometers I travel every year. It's quite a lot. So I would like to start this presentation by acknowledging Jochen for his kind invitation. Actually, we met several years ago in CIR 05. It was my first presentation abroad at a conference like CIR. It was held in Brazil. And we also had great times, mostly during, like he said, during the ACIR series conferences. We were supposed to meet last year in Lisbon to attend this conference, but due to COVID, we ended up not doing anything besides presenting our works virtually. And the same will happen this year as ACIR will be hosted online, as we were briefly talking. So Jonathan, thanks a lot for your introduction and for invitation to be here to present our work. So it's my pleasure to be here from Portugal to the world. I know you have locations, like you said in the introduction, from New York to Singapore, obviously growing also from London, where I believe some of you might be right now. So thanks a lot for joining us today for this presentation about YAKE keyword extractor. I will also have a look at other tools, but mostly about YAKE. So YAKE is the result of a joint work with a team consisting of a few researchers. So Vitor Mengerovic, you can see here at these pics, who has implemented the Python package, designed part of the solution, and was responsible for putting in practice the experimental part of the work. Ariane Pasquale, the man behind the demo and a valuable researcher who has worked with us, did also an internal at a Signal company, who some of you might know very well. And it's now it's just left us and moved to Brussels to a new company. And also Alípio Jorge, Célia Nunes, and Adam, with whom I could extensively discuss the idea and the design of the algorithm. So I'm really thankful to all of them and to their contributions over these years in order to come up with YAKE. So the first question here that I would like to pose is, why the heck did we develop YAKE? Was there any motivational reasons? Well, the short story is that I don't like to be dependent on third-party libraries whose internal, properly I would say internal behaviors, I'm not aware of. So I should also say that upon conducting my PhD, Python didn't have the recognition that it has today. So if it had, I could have taken 2 PhDs instead of 1, as my colleague Adam often says as a joke. So in those old days, which are not that long, we were neither aware of Python nor of its libraries. So it was quite challenged to find some good keyword extractors. And I thought this was a very good reason to start thinking on developing something that could be used without much difficulty in the projects, in our projects and in the projects of the lab. So there are obviously scientific and motivational reasons too behind this decision. The fact is that over the years, it became evident that extracting knowledge and insights from so much data will be a huge challenge for those interested in making sense, let's say, of an event. And this is partly rooted in an unprecedented number of documents that are published on a daily basis, ultimately creating the feeling of information overload and making it difficult, above all, for people to quickly understand the story of a topic beyond the amount of information that regular people can digest and simply keep in their minds. This exponential increase also that we can see in the volume of data, known as big data, the diversity of news, and an increasing number of sources, including social media, make it, however, virtually impossible for common people to access, manage, and I will say memorize information over time without resorting to auxiliary tools, right? So it's referred by Adam, an American poet in 1941, the greatest problem of today is how to teach people to ignore the irrelevant, how to refuse to know things before they are suffocated. So far too many facts are as bad as none at all. The extraordinary thing here is that this sentence has almost 80 years, and I would say it's now truer than ever, right? So naturally, there was also a scientific reason behind the development of YAKE. We did believe that we could do something interesting in the field. While the task seems pretty simple, to output a set of keywords that best summarize the main topics in a document, the fact is that this is a very difficult problem where most of the systems still, and I believe they will still present low effectiveness in the coming years. So this paper that we can see here from InSpec collection, which is a well-known collection when it comes to evaluation purposes, says it portrays how difficult it may be to reach a consensus on which are the most relevant keywords of a text. So by looking here at the picture, we can see marked as gray color keywords that reflect the result of a manual process where human annotators were asked to choose what are the words that best characterize the document. So we can have a look here at the document and see keywords such as linear constraints and set of natural numbers, which I would say don't offer many doubts as to its relevance. But choosing, for instance, a minimal generation set that we have here, instead might be questionable, especially when minimal set of solutions, which is quite similar to the other one, is simply left out. And what about compatibility systems that we have here in the title? So I'm pretty sure that if this document is given to any of you, we would get kind of different words, and which naturally has to do with the philosophical notion of what is important for us and what matters for us. And this, I think this is just the list of our problems when tackling the issue of extracting relevant keywords from a document. What if our system is able to retrieve a partial match instead of an exact one? For instance, which one gives us more information? Linear Diophantine equations, which is here, or system of linear Diophantine equations? Actually, these are tough questions, and I don't have a proper answer to give you. What all this says is that developing a system that pleases everyone, well, it is simply not. It is simply not possible, and it's out of our control, at least as for now. And that might justify the huge number of proposals that came up to light during the early days of computation, but I will say mostly during the recent years. I'm usually requested to review papers related to this matter, mostly after the emergence of YAKE, so after 2018, and we are just talking a 2-year time period. And I have seen dozens of new proposals to come up every year, every month. It's incredible. So keeping up to date in this particular domain, and I would say likewise in the general field of artificial intelligence, is not an easy task by these days. And again, it's an information overload problem that we have to deal with. On top of the hierarchy, we have two dominant approaches. So we have unsupervised approaches, which interpret data based only on input data, and supervised ones, which develop a predictive model both based on input and output data. Then on the left list, we have graph-based approaches, statistical-based, and more recently, embedding ones. Okay? During the last couple of years, we have seen lots of proposals under this category. So statistical-based ones, where you can find proposals such as term frequency, inverse document frequency, or KP minor, which is a very well-known statistical unsupervised approach, or YAKE. Well, like I was saying, they are poorly unsupervised models which rest on some heuristics and thus do not even require any training stage, as embeddings models, for instance, do. So on the right side, we have deep learning models, and those that are most traditional, like classification models, which assign observations into discrete categories, if it is a keyword or it's not a keyword. A great example of this, perhaps one of the most successful at date keyword extracting models, and at least with lots of citations, is the KIA keyword extractor, which is a binary classifier that builds on top of the probabilistic naive Bayes algorithm method. And we also have regression models, which estimate or determine the relationship between two or more variables, and where, as everybody knows, output or may output continuous values, okay? And this brings us to the following question: to supervise or not to supervise? Well, it all depends on what we want. So generically speaking, unsupervised models such as TF, IDF, or YAKE show worse effectiveness when compared to supervised ones, which on the other side also have their cons. So they require access to a ground truth data set, which may take time and money to build. Solutions may not generalize well under a different domain than the one used during the training stage, which is also related to the fact that training time may be a time-consuming process, and that may be problematic for for some institutions and for some organizations where where budgets are very low. So for those interested in getting to know more about keyword extractors, I highly recommend having a look at the tutorial that we gave last August on ACII. There is also a great survey published by Erini and Grigoris, two Greek colleagues of mine. We were also part and led the tutorial, and they greatly summarized this topic in these articles, so I highly recommend you to have a look at it. So roughly speaking, the process of extracting keywords from a document or a collection of documents, in some cases, entails a couple of steps. So first, we should start by preprocessing the document applying generic NLP tasks, such as sentence splitting, tokenization, lemmatization, part-of-speech tagging, or name entity recognition in some of the cases. And next, we aim to define a couple of candidate terms. So one possibility is to consider an n-gram sliding window, like we do on YAKE algorithm. We will see that in a short time. But part-of-speech sequence-based rules can also be followed. So afterwards, one needs to define the features in which the developer's opinion he thinks that better convey the notion of relevance. And this can be internal to the collection, such as, for instance, some of the features that we use on YAKE algorithm, but external, such as IDF from TF-IDF, or even the use of knowledge bases. So the final step in this process is to rank the keywords according to some algorithm, be it supervised or unsupervised. So once this process is concluded, one needs to evaluate the effectiveness of the system. And in this step, we have two options. So manually evaluating the results is something that can be done by humans simply after obtaining the results, but it is kind of an expensive task, and it is not appropriate for any kind of parameter tuning because it is a posterior analysis. So there may be a better alternative solution, which it's also expensive sometimes, is to conduct an automatic evaluation. Expensive in the sense that we might not have the necessary data set or ground truth data set, which is not the case in keyword extraction. In this case, the results of the algorithm are compared with those of the ground truth data sets, of course. So when people ask me whether YAKE is or not appropriate for using as part of their systems architecture, my answer revolves around the following. It really depends on what is your problem. So if you are looking for high effectiveness, my suggestion will be to go directly into supervised models, particularly those proposed more recently and involving embedding models and neural networks. However, if you are looking for an unsupervised approach, which does not require any training corpus, a domain and mostly language independent solution that works with domains and languages for which, and this is very important, there are no ready keyword extraction systems or even linguistic tools such as name entity recognition or part-of-speech taggers. Also, a solution that does not discard interior stopwords such as, for instance, Game of Thrones. A solution that is term frequency free in the sense that no conditions are set with respect to the minimum frequency of the candidate keyword in the text or in the number of sentences that it occurs. And also an open source solution that is people are ready to play with, then in that case, YAKE can be an appropriate solution for the problem of that person. At least I will challenge the researcher to give it a try and see how it goes in terms of evaluation, of course. Okay, so how does YAKE works? So similarly to the general task seen before, YAKE is fed with an input text. So first we begin by preprocessing the text, which is the first step. Then on step 2 is the feature extraction process. Step 3, the individual term score. Step 4, the n-gram score. And step 5, the deduplication and ranking phase, which will be responsible for the output of the final list of keywords. So these are the 5 steps that compose and that entail our methods and our algorithm. So in particular, and for the first step, we apply common techniques such as sentence splitting, tokenization. And in addition to these, we also take some special words, for instance, uppercase words and numbers for each. A special treatment is given later on in our method. But following, we devise 5 term features. So the first one is T-case. So the casing aspect of a term is obviously an important feature when considering the extraction of keywords. It's natural to consider them as a feature. So in our approach, you give an extra attention to those words that appear with a capital letter, except obviously those that are beginning with sentences. So the more often the candidate term occurs, the more important we consider the term to be. However, we don't believe that there is a linear relationship between the importance of the term and the number of the times it occurs with a capital letter, and that is the reason why we divide it by its slot. Okay? So another indicator is the importance of a candidate term, its position. So the rationale here is that relevant keywords, and we saw this on some literature, we were based on some literature to came up with this assumption, that they tend to appear at the very beginning of a document, whereas words occurring in the middle or at the end of a document tend to be less important. Obviously, this does not happen all the time, but I would say this is particularly evident for 2 kinds of publications, which are news articles and even research articles, where the abstract and the introduction may play an important role. So our assumption here is that terms that occur in the early sentences of a text should be more highly valued than terms that appear later on. So instead of considering a uniform distribution of terms, our model assigns high scores to terms found in the early sentences. So the result of this is an increasing function that increases smoothly as candidate terms are positioned toward the end of the document, meaning that the more a candidate term appears at the beginning of the document, the lower its T position value is. But conversely, terms more positioned toward the end of the document, which are likely less relevant, will be given a higher T position value. Then as the third feature, we have the TF norm, which reflects the belief that the higher the frequency of the candidate term, the more important it will be. Yet, this does not mean that the importance, again, is proportional to the number of times a term occurs, so as to prevent a bias towards high frequency in long documents. The TF value of a candidate term T is divided by the mean of the frequencies plus 1 times their standard deviation, okay? So our purpose here is to value all those candidate terms whose frequencies are above the mean, balanced by a certain degree of dispersion that is given by the standard deviation. Next, as a 4th feature, we have TRL, which aims to determine the dispersion of a candidate term with regards to its specific context on the left and on the right side. So we rely on the assumption of my former supervisor, Gael, who states that in a paper that he has published, that the higher the number of different terms that the candidate term occurs with, the less significant the term will be. And this is what VL to the left and DR to the right account for. So then the L as well as the R are then multiplied by the term frequency divided by the maximum term frequency among all candidate terms that occur in the document, in order to penalize candidate terms that co-occur with high frequency, as stop words do, or even non-discriminant terms do. Okay, and we do this on the left and on the right side. So in practical terms, I will say that the less relevant the candidate term is, the higher the score of this feature will be. And like I was saying, stop words and similarly non-discriminant terms tend to obtain a higher score under this feature and under this condition. So finally, this sentence, which is the last feature that we devised and included in our algorithm, quantifies how often a candidate term appears in different sentences. So it reflects the assumption that candidates which appear in many different sentences have a higher probability of being important. And this closes step number 2 of our method. And then it's time to score individual terms. So once these features, these 5 features are computed, we are now ready to determine these individual scoring function. And to compute this score, we gather all the feature weights into a unique STC score, which is an heuristic measure, right? So the smaller the value, the more significant the 1 gram will be, and this stems for the fact that we have a division in this equation. So looking at it, at the equation, we can observe that both TF norm and T sentence are divided by T relevance. So the idea here, the underlying idea behind this mitigation is to assign a high value to 1 gram terms that appear frequently and in many sentences, likely indicative of the importance, but as long as they are relevant, that is, as long as they have a low T relevance score. And that's the reason why we divide it here. Indeed, some terms we might think may occur numerous times and in many sentences, and yet they can be useless, as is the case, for instance, of stop words or non-discriminant words. So we believe this should be penalized, right? So achieving a high score on TF norm and T sentence is an important indication of a term's importance as long as T relevance has a low value. And likewise here, the position of a term in sentences occurring at the top of the document is an important feature that we consider in this measure. What is interesting to note here is that this can work as an individual scoring function, like we have, for instance, with TF IDF. So if we look at the table, we can observe that at the top 30 terms with lower STS score, we have a considerable number of words or parts of keywords that were considered relevant by the human annotators when asked to classify this example from inspect collection. And conversely, on the contrary, when looking at the bottom 30, those with the highest score, we can only see there are 2 relevant words. And so this is quite interesting because it shows the importance of this score on considering with lower scores good words, relevant words, and with higher scores worse words. But the problem here is that we are just still thinking and working only with single terms, and keywords may be composed and consisted of more than 1 term. Okay, so once we have these scores, we are now ready to form the list of n-grams that will give us the final list of keywords, where n can be a number. But experiments conducted show us that most of the keywords are consisted of terms up to 3 terms, of phrases up to 3 terms. So we compute the score of each candidate keyword by considering its individual score. As you can see in the numerator, we have there the individual score, the ST. So in particular, we begin by multiplying in the numerator the STC scores of the several terms that can constitute the candidate keyword. Okay? So one potential problem of this product, however, is that the length of the candidate keyword, given we have here a multiplication with values very close to 0, may highly impact its scores, thus favoring lengthy, relevant candidate keywords as opposed to short ones. So to reduce this impact and extract keywords irrespective of their length, we compute the final score by dividing the numerator that we have already discussed by the sum of the ST scores weighted by the candidate keyword frequency key F. And this is very important, this part of the key F that I'm showing here, because this enables us not only to mitigate the problem that I have spoke a couple seconds ago, but also to differentiate between candidate keywords, which are constituted by the same terms, keyword extractor, but have a different order, keyword extractor or extractor keyword. So the rationale is that a candidate keyword that appears more often, keyword extractor, should be given a higher score than a candidate keyword, for instance, extractor keyword, that despite being formed by the same sentences, does not occur that often, okay? And so this is an important part, obviously, of the work, because it will give us the final score for the candidate keyword. And in the last step, which is step number 5, we have the duplication and ranking, which just ranks keywords based on the computed previous measure through ascending order. So the lower, the more important the keyword is considered to be. And we select the top key keywords, where top is a parameter that people can choose. And we try to remove duplicate keywords through a duplicate method, defining here a threshold. So to evaluate the effectiveness of our system, we tested it on 20 different document collections. So our aim here was to understand how YAKE behaves under a large number of scenarios. So the collections included 5, as far as I remember, 5 different languages, 6 or 7 different domains, and different kind of documents, from reports to other things. And then to understand which were the best parameters of YAKE and the effectiveness of all the approaches from a single unified view, we also consider, in addition to each data set, the union of all the data set documents into a single aggregate collection. And so the plot that we have here just resembles the precision recall curves under that single aggregate collection. However, instead of merely merging all the documents indiscriminately, which will result in having a collection obviously dominated by the biggest individual data sets, we applied a resampling technique called random oversampling. Obviously, today we also have some data augmentation techniques. And to this purpose, we randomly duplicate the document of each dataset until all the datasets have the same number of documents as the largest collection we had. And that collection was scrapped in 2009 with more than 2,000 documents. And this means that each of the 20 datasets that we consider will see their documents randomly duplicated until they have more than 2,000 documents, thus creating an aggregate collection of 46,000 documents. So by doing this, we guarantee a fair representation of each dataset in the aggregate collection. And the results seem to confirm that YAKE has a good behavior, but again, this depends on a bunch of factors, including the dataset used, the metric used to evaluate it, the problem. Well, it always depends on a number of factors. One of the interesting things of YAKE is that we have a demo, which makes it easy for regular people and for common people to play with. So YAKE is available online, and you can be easily used by anyone interested in extracting keywords from single documents through this web address that you can see here. While in the web page, people can start by providing some random text from which to extract keywords. But in this example, I will resort to our initial running example, which was this text that I borrowed from Inspect collection. So recall that gray color words were manually annotated by humans as the most relevant ones. So this is the ground truth. Then we have green colors, which are those retrieved by YAKE, and that match or partially overlap the ground truth. So up front, we have here linear constraints, and then we also have here linear Diophantine equations and natural numbers and minimal generation sets, right? But we also have natural numbers, okay, which is only partially overlaps the ground truth keywords, which was a set of natural numbers. But on the other hand, the system was not able to determine those still marked as gray, so strict inequations, upper bounds, and non-strict inequations. And finally, it also detected 3 other keywords on the opinion of YAKE, which were a set of solutions, systems, and considered types of systems, which are not at all keywords considered, at least by the human annotators. A word cloud is also given to the user, highlighting the most relevant keywords, and this resembles what we have just read in the text. The higher the size of the text, the more important, obviously, the keyword will be. And again, we see here highlighted the big emphasis: linear Diophantine equations, linear Diophantine equations, and so on and so forth. Finally, when playing with YAKE, with the demo of YAKE, one can see the top 20 keywords of it and compare it against the results of RAKE, which is another well-known statistical method. Previously, we also compare it to IBM Watson when it was free, but now it's no longer free, so we just remove it from the interface. We are talking obviously of research solutions. There are plenty of solutions in the markets, being probably the most well-known is from IBM Alchemy solution. So in addition to these, users are offered the chance to give us input a web address. Here I'm giving some related news article to neuroscience news. And similarly, as before, we get an annotated text. So without reading it, we can observe that this has something to do with disease. Probably this is some research paper related to Columbia University Medical Center, and that tackles brain and aging. For those interested in playing with YAKE, we have a Python package within an interesting number of stars and forks. As of the date of yesterday, we had more than 500 stars and approximately 100 forks, which is not bad for our realm. And we also provide the users an API available for free for those who are not proficient with Python or just want to play these on top of another programming language. We also have a YAKE version available at Google Play, which was developed by some undergraduate students of mine from the Polytechnic of Tomar. We have more than 1,000 people who have already installed the app, which is also a good indicator. Playing programmatically with YAKE is quite easy. So to start, you can install pipgit. You can type pipgit to install it. Then you have to define the text. And here you have to import the library, and that's all. Now you need to iterate over the keywords retrieved by the system. So be aware that we haven't read the text, and still we can figure out that this might be related with Kaggle platform. It refers to CEO Antonio Goldblum, which apparently is co-founder, and it's related with Google. If we want, we can also play with the parameters of the system. By default, we don't need to do that. Another interesting thing here is that we can ask the system to highlight the keywords with the tag KW. Okay, so as we can observe here that on the retrieve text we have the keyword Google tagged with this tag, labeled with this tag, and all the other keywords are labeled with it. And this might be important for people playing with HTML because you can also customize with your own tag and, for instance, with your own class. Like I told you before, this is mostly a language independent solution. And in this case, I'm just showing that it will print out and will be able to extract information from a Portuguese text. You can also use it through the prompts, through the command line. And like we saw in the interface, we can also extract the keywords from an API. Okay? So here the difference is that we receive a JSON object, and now we are offered the very same possibilities. We can iterate over by the keywords, again, the highlighted feature, and we can even extract keywords from the web address, from a given web address, like you've seen in the interface, and the result will be the very same. Another fancy thing is that we resort to an external library, so giving users the chance to create a fancy word cloud through Matplotlib and through word cloud third-party library. Okay, so here is the word cloud about a Portuguese text retrieved by providing the system, the API, with a web address. Okay. So if you're interested in getting to know more about YAKE, I highly recommend having a look at these 3 papers. So the first one describes the method to a usage extent, as it is a journal paper. You can find there many answers to some of questions that you might have. Besides discussing them with me. The second one is the short paper presented in 2018 at ACIR, and the third one describes the deal. So now the question here is, why are keywords useful? Is it just a matter of annotating text? I put this slide here because lots of people ask me, why is this useful? It's more than that. It's not only to annotate text. As a matter of fact, this kind of systems can be very useful for a bunch of text. And to have a look at some, I borrowed this picture from a survey paper, a recent survey paper that I also recommend you to have a look at. Very good paper. And this can be important, for instance, to document clustering, to document summarization, information retrieval systems, which is an area that me and Johnson appreciate quite a lot, document indexing, web mining, search engines, which is again related to the task of information retrieval, query refinement, web logs, recommender systems, opinion mining, relevance feedback, ontology. I will show you an example in a couple of minutes, information extraction, name entity extraction, and topic analysis. So as you can see, it can be used over a number of different areas. So over these 2 years, after the emergence of YAKE, we are glad to see that it has been used by some external projects. One of those examples is the Python key phrase extraction toolkit. I'm not sure if you are aware of it, but I highly recommend you to have a look at it. This is a great tool which offers users a privileged way to extract keywords through a number of methods that are listed here. One of those methods is YAKE. This package was developed by Florian Baudin, a French researcher. So playing with this package is quite easy. Anyway, it might be, okay, it's running, might not be updated with regards to the original implementation, as is the case of YAKE. As I highly recommend people, at least in the case of YAKE, to resort to our Python package, given that we have it freely available to everyone. But looking at the video, we can observe that how simple it is to extract keywords from this running example that we have. I have also recently added a key phrase extraction package to our GitHub account and developed a Docker image so everybody can play with it. What is this? So this is a tool that makes use of a Python toolkit, the one we've seen in the last slide, but use it to extract keywords from those 20 data sets that we use in the evaluation stage. So if you work in this area, you might have one. You might want to see this package. YAKE has also been studied under Kaggle live coding in a project conducted by Rachel, which aimed to use YAKE as a means to reduce her workload in reading the increasing number of forum posts that she has to deal with every day. And more recently, it has been integrated on John Snow Labs, which is claimed to be the NLP platform most used nowadays in the business domain, at least as they say. And you can find a live demo and Google Colab and their detect key phrases snippet to play with their implementation of YAKE. Okay. It has also been used as a tool in some research projects over different dimensions. For instance, a recent paper published on ACL used it for evaluation purposes under a mechanical Turk process to evaluate the quality of a short transcript of recorded speech. So in particular, YAKE has been used to select the passages to show to the Turks, to the people. Has also been used to help in the process of constructing a text conversation dataset, where YAKE is used to extract keywords from both context and responses, to select the most important passages of a text in a work that aims, again, to generate texts upon some input data, and used together with the TF-IDF score to access the importance score of a token in a recent published paper that tackles the problem of text generation. Also used as a keyword extractor to select important keywords from Arabic infectious diseases articles, which are then used as input to create a medical ontology. And here, one of the good characteristics of YAKE, the fact that it can be applied to different languages without much effort, and used together with other keyword extractors, an ensemble of keyword extractors within a paragraph completion task work where keywords are used during the training stage to feed one part of the system that aims to predict topical content keywords. So these were some examples that of the use of YAKE externally, but it has also been used internally in some projects that we have developed. So specifically in Time Matters, which is a temporal summarization that aims to summarize topics over time. Tell Me Stories is available online for anyone looking for a temporal contextualization of a given topic. And the first link we have here is built on top of the Portuguese web archive. This is our native application. The second one is an adaptation of our system that we built on top of the Signal Media dataset, which entails more than 1 million articles from 1 month period, and that Joshua knows very well. So on accessing the interface, the user will be offered several illustrative examples. In this case, however, I will query the system with a new topic, which is climate changes. Thus, after the query is issued in the system, you are prompted with information related to the number of documents that we could find. And next, you will have access to the timeline from which we can navigate in between the different time periods and the results interface. These particular results of Signal are not clickable, but they are on the native version of arquivo.pt, where you can have access to the entire document the same way as it was preserved in the past. We have here some very interesting results. This was from 2015. So here we have Obama says world must reach climate deal in Paris, and then we can move forward to 13 September, and we can see some other information regarding Paris climate talks, our last chance, and hold the climate change history. And here again, moving forward, we have here a reference to Pope. Pope had to the climate talks as rare word. And also Bernie Sanders neglects climate change. In addition to this, we also have a word cloud that shows you the most relevant keywords related to the search topic. And while you can imagine that the YAKE is used to generate this word cloud, the fact is that instead it was used to select the most important sentences of the text. And how so? Well, we just consider each sentence as a potential candidate keyword, and that's how our system selects the most important and the most relevant sentences among a huge number of sentences. So if you are interested in knowing more about Tell Me Stories, I highly recommend having a look at these two papers. The first one describes the method and will be published soon, next year, integrating in a Springer book dedicated to the past web and exploring web archives for those who are interested in these matters. And the second one describes in more detail our demo. And finally, and more recently, we have developed time matters, which is also available online under this web address. Again, the input here is a text, so the user can feed the system with whatever text he wants, from whatever language he wants, and just need to press here the red button, tag dates, and the result will be a temporal annotated text where temporal expressions are annotated according to their temporal relevance. So here we use YAKE to detect the relevant keywords in the text. And then relevant temporal expressions are scored with regards to how close they are to the keywords through a co-occurrence measure. One of the fancy things here that we have here is this storyline component, which again uses YAKE to give the title, which is extracted from this short story. And this title will then be used to query the arquivo.pt search service as a way to extract related images over the past to this topic. And here, obviously, we can then just move forward in the calendar and see the other parts of the story. So this demo has just been accepted for presentation at the ACR 2021. So more details about the 8 may be found soon in the paper. As a side note, I would like to give some pointers on a number of related things that you might be interested in, and that somehow is related with this talk. I'm an editor of the guest editor board member of the IPM journal, which is a high impact factor journal. So you're more than welcome to submit your work there. In January, next January, we'll be organizing the AI for Narratives workshop. It will be online, says be our guests. And we are also organizing the 4th edition of the Text to Story workshop under ACR umbrella. So call for papers is open until mid-January. Says please consider submitting your work there if you see that it is related with some of these topics, such as temporal information extraction, event identification, causal relation, storyline visualization, temporal aspects of storyline, credibility, fact-checking, bots lines, information retrieval models based on storyline evaluation, so on and so forth. And we are also at the end of the first year of the Text-to-Story project, which aims to extract journalist narratives from text and representing them through alternative languages. So it's my duty to thank the Text-to-Story project. And with this, I conclude this presentation. Thanks a lot. I hope I didn't take too much time.
Perfect timing, Ricardo. Perfect timing. Thank you so much.